et bienvenue à ce webinaire de la série sur la gestion intégrée des ennemis des cultures ou GIEC. Cette série de webinaires vise à accroître le transfert de pratiques de GIEC auprès des producteurs et productrices agricoles par les conseillers et conseillères. Merci d'être avec nous aujourd'hui en si grand nombre pour ce webinaire portant sur la pulvérisation efficace des pesticides. Tout d'abord, cette activité vous est offerte gratuitement grâce à un financement du programme de partenariat pour l'innovation en agroalimentaire en vertu du partenariat canadien pour l'agriculture, entente conclue entre les gouvernements du Canada et du Québec. Pour les agronomes, dans le cadre du règlement sur la formation continue obligatoire des agronomes de l'Ordre des agronomes du Québec, la demande d'accréditation a été faite et l'information sera déposée sur la page web de l'événement prochainement. Aussi, pour ceux qui aimeraient obtenir la présentation PowerPoint, celle-ci sera déposée en format PDF sur la page web dédiée aux participants. Ils seront également déposés divers contenus informatifs. Le lien pour y accéder est dans le courriel que vous avez reçu pour le branchement au webinaire. Nous pourrons vous le retourner au besoin. Vous n'avez qu'à vous adresser par courriel au service client du craaq. Ce même lien sera également déposé éventuellement sur AgriRéseau à la page web de l'événement. Maintenant, passons à notre conférence de ce matin. Ce webinaire vous est présenté par M. Tom Wolfe, spécialiste des traitements par pulvérisation et consultant chez Agrimetrix Research and Training. Tom, I invite you to share your screen while I'll introduce you. Tom Wolfe est un spécialiste des traitements par pulvérisation basé à Saskatoon. Sa carrière de chercheur à Agriculture et Agroalimentaire Canada, jusqu'en 2013, a été consacrée à améliorer les technologies de pulvérisation agricole. Il poursuit ses recherches et la diffusion des connaissances comme consultant au travers de son service sprayers101.com. Tom, the floor is yours.
Merci, Marie-Ève. Thank you very much. Can you see my screen?
Yes, everything's fine.
Perfect. Thank you very much. Welcome, everyone. Thank you for joining us today. My name is Tom Wolfe, as Marie-Ève has already said. I am in Saskatoon, and I am looking forward to spending the next 90 minutes with you. I also want to thank Marie-Ève and her team for working hard to deliver this webinar to you. We worked for quite a long time to get the content and all the resources together so that this could happen. So thank you, Maria, for that. We have a lot to cover, and I will try to do it as well as possible in the time that we have allowed. There will be about 15 minutes of time for questions if everything goes well. But there are three main topics. The first one will be talking about preparing the spray mixture. We will talk about water quality, mixing order, and a little bit on adjuvants. We'll then move to nozzle selection, and we'll talk about the importance of the right nozzle. We'll give specific recommendations for conventional and pulse width modulated nozzles. And finally, we will end on application timing. We will talk about spray drift. We'll talk about inversions and finish off with some productivity, some logistics. So hopefully that'll be useful for you. Let's start with water quality. Water quality is a topic that is becoming more important. We are paying more attention to the kind of water. And of course, we're spraying a more wide, a larger amount of different products, some of which may be sensitive to certain water qualities. I have to tell you a story. About a year or so ago, I drove to Alberta, and I was driving down Highway 3, which is in southern Alberta towards Lethbridge, and I saw this tanker that was parked in a lot beside the highway. So I drove in to just visit with him and ask him some tricky questions. I'm always trying to learn. So he was filling up with water from the irrigation project. It was municipal water, so it was treated. And he filled up about, I'm estimating about 6,000 or 8,000 gallons of water, and he said it would take him about 30 minutes to fill that tanker full. I noticed that he had a Crimson on his tanker. A Crimson is a water conditioner. It removes hard water cations. And I asked him why he was using it because he was filling up with what I thought was good water. And he said to me, we're doing it as an insurance policy. We're doing it to be sure that the water is good for spraying. We don't want to take the risk. The cost of adding the crimson is acceptable to us. So I found that to be quite interesting. Now, I do think it's important to do a test. I think everyone who uses water, uh, not from a municipality, but certainly from their own farm, from a well or from a pond, should have a water test. And they can be quite confusing. So I thought what we would do is spend some time going over what some of these words and numbers actually mean. So in the first case, I want to start with turbidity. Turbidity refers to suspended solids such as clay, silt, or organic matter, and it's very common in surface waters, ponds, dugouts, and particularly after a rain. They can bind, neutralize glyphosate and diquat, which is Reglone for desiccation. Those are the two most common problem herbicides. They're usually not in a test result, but it's quite visible if the water is turbid. And if you do have turbid water, it's possible to treat the water with a product called aluminum sulfate. I grew up on a farm. We had pond water, and we did use aluminum sulfate on our farm with great success. It allows the suspended solids to coagulate, that means move together into larger globs, and then to become so heavy that they fall out. So aluminum sulfate should only be used in a pond. It should not be used in a tank because it will still be present in the tank and may become resuspended. Here's some images of water that is turbid that was treated with aluminum sulfate. And you can see that as time goes from left to right, that the water becomes clear. So coagulating agents like that are quite useful if you are going to be spraying products that are sensitive to it. But the most common and really the first test that we look at when we look at water quality is conductivity. Conductivity is an indication of how many solutes are present in a tank, in water, and they can be calcium or magnesium, the hard water cations, but they can be anything. They can be nitrates, sulfates, bicarbonates, anything that has a charge will show up here. We typically will say if the total dissolved solids or the conductivity is less than 500 parts per million, that the water is good. So we don't really have a problem. But if it's more than that, then we simply need more information because it doesn't tell us what's in the water. So that requires further testing. Conductivity and total dissolved solids are similar. They are mathematically related. They're about 60 or 50% different from each other, but they can be used as an equivalent more or less. The second parameter that I look at is pH. I have to be honest, pH is not as important as people think it is. So usually the pH of the water is good, and we usually are looking for something between pH 6 and 8. We very rarely see numbers outside of that. I will show you some test results today that'll be a little bit higher, but they're not problematic. So pH is important for two main reasons. The first one is to make sure that the herbicide or the fungicide or the insecticide is soluble, and that makes it easier later for it to be cleaned out. And that's the main reason. The second reason that pH is important is to prevent something called alkaline hydrolysis. Alkaline hydrolysis is the chemical breakdown of the chemical. And it can happen, but it's not very common. And if you have the wrong pH in a tank mix, it can be a big problem. Wrong pH can be the reason why a tank mix just simply doesn't dissolve properly. Let's look at some examples. I'll start with half-life. So this is a table that I made, which contains information about 10 or so herbicides. On the left side here, you can see them and their active ingredients, and then what I found in the literature about their stability at various pHs. And the result was that the majority of the herbicides are in fact quite stable at a variety of pHs, low and high. In some cases, at extremely high pH, the half-life is quite short, but usually the half-life is days long, many days long. The only example that I found that is something is not stable at pH above 7 is gramoxone or paraquat. This is a product that is still common in the US, but it is not commonly used in Canada anymore. I believe it was deregistered a few years ago because of its safety concerns. A much bigger problem is water solubility. So again, here I've listed some herbicides by trade name on the left. These are the active active ingredient names. And here is the mode of action group. Most of them are in group 2. And then I listed 3 different pHs, an acidic pH, a neutral pH, and an alkaline pH. And look at some of the yellow highlights here. Tribenuron Express, a common product for pre-seed burn-off, often mixed with glyphosate, very low solubility at low pH, very high solubility at high pH. This is common for many of the other group 2 products. Simplicity is another example, and Frontline, very, very low solubility at acidic pH, but very good solubility or better solubility at least at high pH. Even group 14, Heat, is the Western Canadian name, I believe. It has other names in Eastern Canada, but it is often used as a pre-seed treatment. It's also used as a desiccant. Very low solubility at low pH, also lower efficacy at low pH. And Infinity, pyrosulfatol, group 27, same story. So we have to be very careful about pH for that reason. And in fact, a high pH is more well suited for most herbicides than a low pH. And yet we talk a lot about adding an acid, for example, to make glyphosate work better. And I would say that the scientific literature does suggest that glyphosate can work better at lower pHs, but it's not much better. It still works very well at neutral pHs. And because we are mixing glyphosate so frequently with other modes of action, for example, we often mix glyphosate with group 2, we often mix glyphosate with group 14, sometimes other groups, and we want to make sure that those tank mix partners work well. And for that reason, I don't recommend the acidification of really any herbicide unless it's recommended on the label. Bicarbonates are the third element that I typically look at. Bicarbonates can antagonize some products, 2,4-D, MCPA, very common products, but only the amine form. The ester form is not antagonized. Tralcoxidum, cethoxidum, clethodim, we know these products as Post and Centurion. The DIMS group 1 products are also affected by bicarbonates, and they may be associated with high pH. In fact, some acids can in fact get rid of bicarbonates. Usually though, we use ammonium sulfate and urea ammonium nitrate. We'll talk more about ammonium sulfate shortly. The most important parameter to look at is in fact total hardness. It's calculated from calcium and magnesium, but also iron, sodium, and potassium can also be antagonizing. But these 3 ions are not reported in total hardness. It is calculated only from calcium and magnesium. So it affects primarily glyphosate and glufosinate. It certainly affects other products to a smaller degree, but it's mostly glyphosate and glufosinate that are affected. It also can affect 2,4-diamine and dicamba, and it is most commonly treated with ammonium sulfate, which is AMS, which is 210024 in the dry form. This is how ammonium sulfate works. It's a white powder. If we have a herbicide that is in the presence of calcium and magnesium, the sulfate ion binds with the calcium and the magnesium and creates an insoluble precipitate. And what that means is it can no longer interact with glyphosate. The ammonium ion actually binds weakly to the herbicide, and it actually improves herbicide translocation. So the sulfate does something useful, and the ammonium does something good as well. And there's a lot of scientific literature that supports that if you add ammonium to a herbicide mixture, it will improve the uptake and translocation. Temperature is the last one. This is not reported, obviously, but it does matter. And low water temperatures can reduce the mixability of most herbicides, especially if there is an oily component to it. And those oils can form films that can work against pulse width modulation plungers. So if some of you have a pulse width modulation sprayer, you have to be careful with water temperature and mixing. High bicarbonates can also make a low water temperature and an oily mixture even more likely to cause problems with PWM plungers. If this happens, you have no choice but to clean them. So it's quite a time-consuming process. I now have a few tests that I want to go through with you. This is typically what you will get from a water lab. And this particular sample is one that is from Alberta. It's from the Red Deer County. It's a pretty good sample. Let me go through how I would analyze this. So first of all, I look at turbidity. It's down here, very rarely reported. This one has low turbidity, so it's clear water. I'm not worried about it, so I'm going to move on. The next one I look at is pH. pH in this case is 7.6, not a problem. We'll just ignore it. The next one, this is quite important, is conductivity. You'll see here we have a 1060 in conductivity and 552 in total dissolved solids. You can see that they are mathematically related and about 50% of each other. That's usually the case. The ratio changes. This is usually, when it's this low, I'm not usually worried, but let's keep looking anyways. So technically, I could stop looking here and say, this water is probably good. Let's look at bicarbonates. Most of the high solubility or the most of the total dissolved solids are from bicarbonates. You can see that's 428. This is pretty high, but it's acceptable. Calcium is also relatively high. Magnesium, sodium is low, potassium is low, and almost always iron is low. What that means is that we have a reasonably hard water here. 500 is considered to be hard, but it's not problematic. So what I would recommend with this water is that it is hard, but otherwise it is okay. I would simply add ammonium sulfate if I was spraying with sensitive herbicides, and I would use this water for spraying. Let's go to another test. This one is a little bit more problematic. We have a good pH, no problem here. We, however, have very high total dissolved solids. This is 27,000. So that's much, much higher. The conductivity is 41,000. This is in millisiemens per centimeter. Usually it's microsiemens. That's why the number looks low. But this is, of course, a problem right now I would say don't use this water. But let's find out why this is high. It is not high because of bicarbonates. It is not high because of calcium or magnesium. It's not even high because of sodium. Those are not low numbers, but they're not very high. It's high because of potassium and chloride. Potassium chloride. This is potash. So this is a typical, or not a typical, but this is a kind of water that could happen in Saskatchewan because we have so much potassium chloride deposits everywhere. So this water is, although reasonably hard, you can treat this level of hardness with ammonium sulfate. This is too high in potassium chloride and do not use for spraying. Let's look at another one. Turbidity here, again, quite low. pH is a little bit higher. Total dissolved solids are high. So we're looking at a fairly high number here with connectivity and total dissolved solids here. So we are curious. Why is it high? Well, the bicarbonates are fairly high. They're over 500. That's a threshold that we are trying not to cross. Calcium also not very high. In essence, this water is very, very soft. If you look at hardness here, it's not hard at all, but the bicarbonates are fairly high. And I would say, let's be careful with this. I would say because the sodium and the bicarbonates are fairly high, I would consider using AMS for this water. So you have to look a little bit beyond hardness itself. Almost finished. Let's go look at this one. pH is good. Total dissolved solids are good. Conductivity is good. Bicarbonates are good. Calcium, magnesium, potassium, and sodium are all good. Hardness is reasonably low. It's intermediate. It is hard from magnesium and calcium, but otherwise the water is okay. And I would just simply say use ammonium sulfate and carry on. And I think this is the last one. Let's look at pH. It's 8. Total dissolved solids are quite high. Bicarbonate is low. Let's find out why the total dissolved solids are high. Electrical conductivity is also very high. Calcium is not high. Magnesium is not high, but sodium is very high. Okay, so now we have the culprit. Potassium is not high and iron is not high. So I'm curious now if there's also chloride, and there is, although the water is not very hard, there is high chloride. And so we have sodium chloride. This is basically salty water. And if you were to taste this water, you should be able to taste that it's salty. That's how much sodium chloride is in here. And you should probably not use this water. It's not hard, but the sodium is antagonistic, and you should avoid this water. I want to give you an alternative. This is a mathematical calculation. If you are sending a water sample to Winfield United that sells adjuvants and herbicides, they will give you a number back that will tell you how much ammonium sulfate to add. And this is the formula that they use. They add the iron and the magnesium and the calcium and everything into the water. It gives you a hardness. And then they have a recommendation for how much ammonium sulfate to add. And the ammonium sulfate is in pounds per 100 gallons. So they're recommending 0.86 pounds per 100 gallons for a water that is actually not very hard. The test is a little bit alarming because it will cause you to add ammonium sulfate to everything, even if it isn't very hard. Even if it's a little bit hard, they say, well, you can get rid of the hardness a little bit with ammonium sulfate. But it is useful for one other reason, and that is if you, for example, had high iron. If you have high iron, in this case, 20 parts per million, that does not change the hardness. And you would think that this test is not very hard. But the iron now has added a fair bit of ammonium sulfate requirements. It has doubled the requirements. And so it is a useful test for identifying those other ions. The old way of doing it was quite different. We used to say, no, don't worry about hardness if the hardness is less than 350 parts per million for glyphosate. And that's for the half-liter rate equivalent. For 700 for the full liter equivalent of glyphosate, 700 parts per million was acceptable. And the thinking was if it's less than that, it's good. Don't worry about it. Now with this new formula, we are thinking of adding ammonium sulfate to almost every tank, and you have to wonder whether it's really necessary. So there is going to be a philosophical divide here. Everything that I've just said can be read, on SPERS 101. So on SPERS 101, Jason DeVoe and myself write articles that are hopefully helpful. And I've written an article here, how to interpret a water quality test. And most everything that I said today is in this article. So hopefully you'll be able to benefit from that. The spreadsheet where you can enter your individual water test results is also in this website, so you can download it and use it for yourself. The options are to use a different well. If you have hard water, use surface water. Surface water is usually soft. Obviously, you can use municipal water. It costs you money. It takes time to get it. But the most common thing, if you have a problem, is to use ammonium sulfate. It's the best water conditioner. It's widely used. It has almost no side effects that are negative. We do not recommend ammonium sulfate with dicamba for soybean, XtendiMax traded soybeans. So because it does make the dicamba more volatile. Reverse osmosis is an option. It is being used by some people, but not very many. It is not very expensive. It's a unit like this will cost about $20,000, but it creates wastewater. It creates about 1 liter of wastewater for every liter that you treat. And so you have to find a way to get rid of this wastewater. Putting it on your grass will kill the grass because it'll be very salty. So be mindful of that. I want to spend just a few minutes on mixing order. Mixing order is important. It's a little bit mysterious. And the best recommendation that I can give you is to follow the label. Most chemical companies have tested mixing order and have a very strong incentive to give you the right recommendation. So that covers the majority of problems. If you don't have a mixing order, I want to share some shortcuts with you. There are 3 of them. And the first one of these is called WALES, WALES. It basically says you should add wet apple powders first, agitate them, then add liquid flowables, then add emulsifiable concentrates, and then add surfactants. It's a very simple acronym to remember. The theory behind it is that the difficult to dissolve product should be added first, and the easiest to dissolve product should be added last. There's another one that's similar. It's called WAMLEGS. It again calls for the difficult products to be added first, followed by agitation. Some more simple solutions later. And then the water-soluble products, this would be also Liberty. And then finally, the surfactants. So the surfactants are always at the end because they dissolve most easily. The third one is called apples. Apples is basically the same thing. It's agitate, soluble powders, dry powders, then the liquids, then the emulsifiable concentrates. These are oily formulations. They form suspensions. And then finally, the solution. So the idea is simple, difficult to dissolve, followed by easy to dissolve. Basically, follow the label whenever possible, and hopefully not have any problems. Remember that pH is a part of this, and high pH would be useful. Mary-Eve, did you raise your
No,
hand for me?
sorry. It's an error.
Okay, I will carry on. Thank you. In summary, I'm recommending that you get your water tested every few years. Water can change over time. For example, we've had some dry years in Western Canada, and our wells are getting a little bit more salty. So it's worth testing. Ammonium sulfate is a very simple and effective water conditioner. The only caveat is, of course, dicamba for XtendiMax treated soybeans. Don't use it for that. I would avoid any pH adjustment whatsoever unless the label requires it. It creates mixing problems that are not good and not foreseeable. And the label is still probably the best piece of information for mixing order. The companies are doing quite a good job making sure that their products mix well. So that is still the best strategy. I want to just spend a few minutes on adjuvants, not too much time. We've already talked about one adjuvant, and that is water conditioners, ammonium sulfate. There are other conditioners that are similar. Most of them are ammonium sulfate based. The definition of an adjuvant is anything that you add to the spray tank to change its biological activity or its application characteristics. And I want to just spend a moment telling you about a product line called activators. These are products that make the spray more wettable, they increase the uptake, they maybe increase translocation, they can make efficacy better. We will not talk about activators today, and the main reason is that I really strongly believe that the label in this case is also the best policy. You know, some of us live close to the United States. The American system has a much different system where they actively promote third-party activators. But the Canadian system is still quite good. Activators have to be approved by the PMRA. And in order for it to be on the label, it has to be shown to improve the performance of the pesticide. And so one of the reasons we don't see a lot of activators is because the companies have not found it necessary, or they have not found it worthwhile to go through that trouble. And I think that that actually has served us well because it has kept our market relatively uncomplicated. If an activator is needed in a herbicide to make it work properly, that will be on the label. They will recommend a surfactant, a methylated seed oil, or in some cases, it will be added to the packaging and will come with a product. So I'm not interested really in studying, maybe this activator can make this herbicide work a little bit better. They're very specific products, and the manufacturers, I think, are worth following here. But there are some things you can do, and the one that I want to just focus on briefly are low drift adjuvants. There's three of them that are quite common. LI700 is the original one. It contains an activator as well as an acidifier. Valid is also made by Loveland. It does not contain an acidifier. It contains an anti-foam agent. And Interlock, of course, by Winfield United, a very common, very popular low drift adjuvant. What do they do? Well, they have a unique ability to allow the small droplets in the spray to be eliminated. So for example, here we have a low drift nozzle, or a regular nozzle rather, with, you can see the drift cloud, and the Interlock has simply reduced the amount of small droplets that are present and has cleaned them up. I'm glad that the company Winfield United shared this video with me, has also included an air induction nozzle. And you can see that it is by far the lowest drift. Now, Interlock might have something to do with that, but in fact, it is very likely the low drift nozzle itself that is to benefit, to credit. Okay, Interlock. Here's some data that Interlock Winfield United shared with me. I don't work for them, but they have a very good lab. They have a very good wind tunnel. They have very good lasers. I trust the science that they do. They are a farmer-owned cooperative. So here's a conventional flat fan nozzle. You can see here Here is the volume median diameter in microns. You can see that they increase the diameter of the droplets a little bit, but they decrease the driftable fine portion about 36%. So that effect depends on the nozzle that's being used. Let's look at a different nozzle. This is a larger nozzle, so it's less drift. It also increases the volume median diameter slightly, but in this case, the overall amount of drift is much lower to start with. And then we have a 60% reduction in driftable fines. So that's quite significant. And lastly, this is with the air induction tip. This is an AIXR, it's a TJet nozzle. Justice is a generic glufosinate or Liberty. Again, same story, a small increase in the large droplets, but a pretty strong decrease in small droplets. So I think it's quite effective across a fairly large range of products. This is now Valid. Valid is a product made by Loveland. We tested this in our own lab when I was working with Agriculture Canada under contract with Loveland. You can see here the herbicide by itself has about 10% driftable fines, and with Valid, it's reduced by probably down to 1/3. With different herbicides, down to 1/2 or so. So it's across a wide range of operating conditions, we feel Valid reduces drift significantly. The best thing about these adjuvants is that they do not increase the large droplets very much. They certainly increase them, but they don't increase them very much. In comparison, the low drift nozzles, the air induction nozzles, they do increase the large drop component quite a bit. And that means that they can reduce coverage for products where that might be important. So while I believe in low drift nozzles, I think we ought to be mindful that sometimes going too big in a droplet is not a good idea for coverage, and a low drift adjuvant might be a gentler way of controlling spray drift. So in summary for this section, low drift adjuvants, they can reduce driftable fines without increasing larger droplets, and that's good. Some low drift adjuvants also change pH, so that's Li 700. Please be careful, make sure that it works with your tank mix partners. And I still believe that selecting a good low drift nozzle will have more effect than adding a low drift adjuvant. And with that as a segue, I want to move into the nozzle topic and spend a few minutes talking about the nozzle world and give you, I think, what I hope is the most recent information that we have on nozzles. Let's first of all start with droplet size. I want to explain to you that nozzles produce a large variety of droplet sizes. So for example, here we have on the x-axis, the diameter of the droplet. On the y-axis, the droplet number, and on the other y-axis, we'll have droplet volume. So let's have a look at the medium spray. On the numerical distribution, when we count the number of droplets using lasers, we can see that the majority of the droplets in a medium spray are very small. In fact, probably 80 or 90% of them are less than 150 or 200 microns. So these are small. They provide excellent coverage. They certainly drift and evaporate. Very few are large. Now, we will convert this to a volume, and this means a mathematical conversion. And now this is the spray volume. In other words, it's the spray dose. So we can see that the whole thing has shifted to the right. And now we can do some interesting things. We can look at what volume is driftable. So less than 150 microns. We can see this is the amount. It might be 5 or 10%. We can also look at what spray proportion is not very efficient. Too big, not enough coverage, etc. Let's look at the coarse spray quality in comparison. Surprisingly, the shape of the numerical distribution is still exactly the same. The vast majority of the droplets are small, and very few droplets are large. The number, though, of the small droplets has reduced by 50%. On the previous slide, we had 4,500 here, and now we only have 2,000. The volumetric distribution is also different. It has shifted further to the right. And we can now see that drift has reduced. But now we're seeing a small increase in droplets that are perhaps too large to work well. Let's go to the extremely coarse spray quality. Again, the numerical distribution is the same. The majority of the droplets are small, but we can start to see larger droplets appearing. Also, the overall number of droplets has reduced, so that means less coverage. That's as simple as that. When we look at the volumetric distribution, it's a little messier, fewer droplets, but look at the dramatic reduction in drift. We still don't have zero drift. We still have small droplets and we still have drift, even with an extremely coarse spray quality. And look at the amount of potential problems on the large side. Too many large droplets, not enough retention, too much rebound, not enough coverage. So that is a problem. I want to show this to you now in a slightly different way. Here are our spray qualities. I've listed the amount of volume that is in small droplets. These are less than 200 microns. So this is from laser data. You can see quite high drift potential for some sprays, but it gets much lower with coarser sprays. I want to look at the rebound proportion. So obviously not very much rebound, but increasing. And then I want to show you the math. So now let's take 100% and subtract 17 and 16, and we get 67. So this is what I would call the usable size fraction. This is going to do the work for you. And interestingly enough, it's not the medium spray, but rather the coarse and very coarse sprays that seem to be doing the best here. So that's very important. We have basically, as an industry in Canada, across the entire country, adopted this practice. We've eliminated the medium spray qualities for the most part because it drifts too much. We have sometimes used extremely coarse when we have to, but for the most part, we are using coarse and very coarse droplets or nozzles that produce these kinds of droplets for most of our herbicide work. Let's look at that in a little bit more detail. The coarse and very coarse droplets can be identified with a color coding that is represented by manufacturers, and they will typically do this. So here's a turbo T-jet. This is a fairly old existing nozzle. It's a very good nozzle. Here you'll see the pressure at which it can operate. Here you can see the droplet size, the flow rates at which it operates. And here you see the spray qualities that this nozzle produces. So if you wanted to use a coarse spray quality and you were going to use a Turbo T 11003, the blue nozzle, you would be able to say that you should be using 25, 30 to 40 PSI, but not above 40. Above 40, you will get into a medium spray quality. You may have excessive drift. Also, with most nozzles, you'll see as you lower the spray pressure and as you increase the droplet diameter, the sprays simply get coarser. That's a common feature. So this information is usually available in sprayer catalogs. If you have a T-jet nozzle, look at T-jet. If you have a John Deere nozzle, John Deere publishes a catalog, and obviously these will be online as well. And that's what the colors mean. All right, let's look at some examples of nozzles that I think you should consider using. The air bubble jet, this is in alphabetical order. This is a common nozzle in Western Canada. It's a terrific nozzle. I'm not sure whether you can get it in Quebec, but it's a good nozzle. It's air-induced. It comes in sizes from 0.1 to 0.6. We use it at intermediate pressures, and it produces a medium to coarse spray quality. It's quite useful. A very popular nozzle is the Greenleaf Air Mix. This is actually manufactured in Germany by Agrotop. This is popular because it has a very good price. Again, the same size, same pressures, and same spray quality. So it's a little bit coarser than the air bubble jet, but this would be a very good general purpose nozzle. Greenleaf Air Mix. The Hypro Guardian Air is also known as the John Deere Low Drift Air, or LDA. Comes in a variety of sizes. It also has a unique size, the 035. Same spray pressure, basically the same spray quality as the other nozzles. These are all considered air induction, low drift sprays. Leckler is a German nozzle. They have the IDK, a compact nozzle that is very much like the other nozzles I've just shown you. It's a very similar, it's a very good nozzle as well. The TJet AIXR is very commonly used around North America. Again, it's basically the same category of nozzle producing similar kinds of outcomes. What TJet has done is they are one of the few that has increased the size of their nozzles. If you should need a larger nozzle, they've now done quite a large number at 10. And so that'll be useful for higher water volumes. I don't want to leave out Wilger. That's a Canadian company. They make nozzles that are not air induced, but they are low drift. They have a large selection of sizes. They have a very large selection of models, and they can produce basically any spray quality that you have in mind. We will look at this nozzle again when we talk about pulse width modulation. For those of you who are new to spraying, I just want to very quickly review what happens with sprayer plumbing. This is how we control the flow of the liquid to the nozzle. It's relatively simple. It looks complicated, but I'll just quickly go through it. All sprayers have a pump that pressurizes the spray liquid and pushes it either to the boom, where it's atomized, or back to the tank. If you need more flow to the boom, you will restrict how much you allow back to the tank. So you'd use valves for that. And this is in a modern sprayer, it's automated. So if you need more flow because you're driving faster, automatically the amount of liquid that returns to the tank is reduced. And that's how it works. In a modern sprayer, it looks more intimidating, but it is actually still the same. The pump pressurizes the liquid. We can reduce the flow from that liquid to the agitator, but it will go either to the boom over here or back to the tank over here. And here is your automatic regulating valve. So if you are driving faster, this valve closes and reduces the return. If you're driving slower, this valve opens and increases the return, and that has pressure effects down here. We're measuring the flow with a meter. We're measuring the speed. We're measuring the pressure. At the end of the whole process, you have a rate-controlled spray. A modern sprayer will increase or change the velocity of the pump, and that is a faster way of changing spray pressure. So if you wanted to then select a nozzle, you would need to have 3 pieces of information. You need to know what the nozzle spacing is on the boom. Is it 15 inches? Is it 10 inches? That's becoming common. Is it 20 inches? That's most common. What is the volume you want to apply? We'll talk in gallons per acre here. Let's say you want to do 10 gallons. And what is the speed you want to drive? So again, that depends. If you say want to drive 14 miles per hour to apply 10 gallons per acre, what is the nozzle you should use? And I really recommend going to catalogs. They have these charts that are very useful. They're easy to use. In this chart, you have 10 miles per hour at the top. You have gallons per acre in the body. You have the nozzle size here. Let's go through this. Here's your 14 miles per hour speed. And we're now looking for 10 gallons per acre. And we have several solutions that we could choose from. And the question is, which one of these should you choose? Some of these have quite low pressures here, the larger nozzles, and the smaller nozzles have quite high pressures. Of course, you should choose the nozzle that has the middle pressure, and that's the 04 nozzle. There's a better way of doing this, and typically I prefer that this upper row here is not miles per hour, but gallons per acre. And you can just pretend to switch. Make this 10 gallons per acre. You can see that the red row is now 14 miles per hour, more or less. So it's the same nozzle solution, it's just a little bit more intuitive. If you do that, if you do it this way, then you can identify your pressure range, and that will correspond to a travel speed range right here. And that's what I find so useful about doing it this way. You can travel as slow as 10, that's 30 psi, as fast as 18, that's 100 psi, or any variant of that. On Sprayers 101, we have these charts. You can download them. They do exactly the same thing. And here's exactly the same answers as I had before. But you can customize this, put your own numbers in here. You can do it in metric if you wish, and carry on from there. If you're an agronomist listening to this and you want to investigate a complaint, you can also use these charts in a very clever way. Let's assume that you have a client who is complaining about grassy weed control. Let's assume that they used a 11005 nozzle. They applied 10 gallons per acre and they drove 13 miles per hour. You can now use this chart to figure out what was the pressure that they applied. Let's do that. Okay, so here we have the 05 nozzle, it's brown. Here we have now the 10 gallons per acre, and we are looking for 13 miles per hour. That's right here. And you can now go back and find out, that was applied at 30 psi. Is that a problem? Maybe, maybe not. If the nozzle is quite coarse already, at 30 psi, it will become even coarser. And as a result of that, it might have been too coarse for the herbicide to provide good coverage for grassy weed control. The pressure gauge is your speedometer. That's really it. I think that's where we're at. Sometimes people ask me, how fast should I drive my sprayer? And the answer is, I say it as a joke, really, you should drive 60 psi. And what I mean by that is the pressure is more important than the speed. If you drive at that pressure, and your speed is wrong, it's too slow or too fast for your conditions, that means you have the wrong nozzle. That means you need to change the nozzle. Don't change your speed because that changes the pressure. And the changing of the pressure could be problematic. So that's the philosophy of it. Now, there's a new technology, and I don't think it's that new. Most of the John Deere sprayers are selling with it. Most of the Case sprayers are selling with it. You can get it on any other sprayer. It's called pulse width modulation. I want to spend a few minutes just explaining to you what this is before we move on to the last section. All nozzle bodies have a diaphragm check valve here to prevent dripping. And in a pulse width modulated system, we replace that diaphragm check valve with an electric solenoid. So this is now an on-off valve that can be used to prevent dripping, but it can also be used to pulse the nozzle. The the solenoid looks like this. There's a magnet here. There's a plunger. There's a seat. There's an adapter for the nozzle body. And when you use this, it just simply pulses really quickly. The frequency that it pulses tells you what the hertz is. So it's usually 15 hertz. It can change. The duty cycle is the proportion of the time that the valve is open. So 100% duty cycle is wide open, and you can usually go as low as 20%. And there's usually a pressure drop across this valve. And when we use it, the beauty of it is that you can adjust your travel speed much more widely than you could with a conventional pressure-based system. So typically in a pressure system, we might be able to go from 30 to 90 psi. We would have a travel speed ratio that is about 1.7. What is that number? Well, this is threefold difference in pressure, and this is the square root of 3. The speed and pressure relationship is a square root relationship. So you might be able to go from 10 to 17 miles per hour. You remember these numbers, they were already in our analysis we did for selecting the right nozzle. The dosage resolution, the entire boom applies the same rate. If you have a PWM system, your duty cycle ratio is about 5-fold. That means your travel speed ratio is about 5-fold. That means You could go much slower or significantly faster than you could with a previous system. This gives you flexibility for slowing down under rough ground or speeding up when the time makes it necessary. And the resolution is on individual nozzles. That means you can run different nozzles on different parts of the boom at different duty cycles, therefore giving different rates. So here is the solenoid in action. You can see it pulsing. Here I'm slowing it down. It's mostly open. You can see it's mostly in the solenoid, the valve. And now I'm going to change the duty cycle and I'm going to change it to mostly closed. So now it's mostly against my finger. And you can see that the frequency has not changed, but the proportion of time that the valve is open has changed. And so what we do now with these kinds of systems is we simply choose a pressure. We choose a pressure that we like, that works well for the herbicide that we use and gives the right droplet size. And we then have a 5-fold pressure range, or duty cycle range, I should say, that gives us a speed range. So it's a wide speed range. We choose a nozzle that runs at 70% duty cycle, and then we can take advantage of this flexibility. So if we want to size the nozzle now for this system, we have to do a trick. So we can use, I guess, a web tool, or we can use this trick. Let's say we want to do conventional rate control, 10 gallons per acre, 14 miles per hour. We've already done this, right? We've identified the possible nozzles. Now let's say we want to do this for pulse width modulation. We would simply pretend that we're oversizing this nozzle. And as a result, we would get about a 70% duty cycle here. And now we are solving for this, and the nozzle that we choose is very likely to be larger. We've chosen a red nozzle before, now we're choosing a gray nozzle. So that's how it's done. You can also go online. There's a very useful website called the Tip Wizard. In the interest of time, I'm not going to spend any time here, but we'll be able to, you should be able to see this just by going to the website. It's very, very easy. So why a 70% duty cycle? You need to have some room to move up and down. You can increase your speed by 30% or slow down by a factor of 3. So that's very, very useful. You can use pressure to control droplet size without a speed change. For example, if you want larger droplets for better drift control, you would lower the pressure. You would then have less flow. You would usually slow down. But now your duty cycle automatically increases by up to 30%, and the speed can stay the same. Let's say you want to do turn compensation. The outside boom does need extra flow, but it needs less extra flow than the inside boom does, or it needs more flow than the inside boom. I think you know what I mean. And so turn compensation simply will not work at 100% duty cycle. You have to have an intermediate duty cycle to allow turn compensation to work well. The rules of thumb are that you can, if you have 5 gallons per acre, this is not a very common volume, but we do use it with glyphosate in a pre-seed burn-off. If you're going at an average speed of this, you use an 0.3 nozzle. If you're going faster, you use an 0.4 nozzle, okay? If you're doing 10 gallons per acre at an average speed of 12 to 16, you're using an 0.6 nozzle, and different versions of that for John Deere and Case. And if you're going a little faster, then you would use a slightly larger nozzle. These are the ones that work well. And so we're coming back to the Wilger Combo Jet. They do have 5 series. I've left out the UR, but ER, SR, MR, DR, and these are the finest. These are the coarsest. And the Wilger Tip Wizard does give you very good help for making that work. John Deere has the Guardian nozzle, also called the LDX. It's also quite good. It's a little bit finer, so you be careful with this one. It may increase spray drift. John Deere also has, for their exact apply system, the John Deere LDM, a terrific nozzle. but it's quite coarse. So be careful with that part of it. Higher pressures are probably a good idea with it. There's another one called the ARAG CFLD. ARAG is a Italian company. They've come into Canada recently, and they produce a very good set of nozzles. And this is one that is gaining some popularity. Okay, I just want to have just a couple of words on water volume. We've talked mostly on droplet size, but in some cases we do have to spray into a dense canopy. And I just want to show you just some small amount of evidence how spraying into a dense canopy, a water volume can really, really help. So in this case, we're spraying into, these are chickpeas in Saskatchewan. I just want to show you in the lower canopy, the 300 liter per hectare or 30 gallon per acre rate was useful in getting more spray down there. It was very powerful in the middle and even in the top canopy, quite useful. So very strong evidence that water volume is a useful tool for getting into a canopy. This is peas. So these are peas we grew in Saskatchewan. We did a small study with this sprayer, and I wanted to show you very quickly these results. In the top of the canopy at 5 US gallons per acre, actually we had what I would call sufficient coverage. It's just sufficient. But 10 gallons was much better, and of course 15 gallons even better. When we went into the middle of the canopy, we started to see a problem, not enough droplets. Even with the 10 gallons, really marginal number of droplets, but the 15 gallons still gave densities that would result in good desiccation or good fungicide. When we went to the bottom of the canopy, almost no droplets there. Even for 10 gallons, I would say barely enough. But for 15 gallons, it might not be very much, but it's certainly the best of the bunch. And if you have disease down there or weeds down there, that's the best way to get there. So in summary of this this second last part, let's quickly go through this. Choose a nozzle that can operate in the middle of its pressure range. And the same is true for pulse width modulation. Choose a nozzle that operates the PWM duty cycle in sort of the middle to upper third of the duty cycle range. And increasing the water volume is absolutely the best way to improve coverage and canopy penetration in our research. Okay, we're going to go into our last section. We don't have much time left, and hopefully we can finish this in time. The traditional drift model is that small droplets plus wind increases spray drift, and that's true. But I prefer to look at it more like energy and force and movement. And if we look at it from that perspective, if we have low energy, we can find ways of increasing energy. If we expose to force, we can find ways of decreasing the exposure to force. And so the best way to control spray drift from droplets is to increase their energy. You increase their size, that creates more energy, or you increase their velocity, that also increases energy. So that could be low drift nozzles. It could be lowering the boom. It could be air assist. All of these keep the droplet velocity high. Exposure to force, you can protect it. There are shrouds that are available. You can lower your boom. You can also slow down and reduce the force that the equipment exerts on the spray plume. You can optimize air blast strength. These are all the tools, and I prefer to look at them this way. When we did some studies, we found that about 20% of the spray that we emit from a sprayer does not land on the spray swath. So for example, when we look at the amount of spray that deposits under the boom, only about 80% of it on average ends up landing on the boom, and the other 20% goes somewhere else. So the question is, where is that place? And so we have this issue. Let's look at where the spray goes. If we look at the deposit under the boom, we measure that. We also measure the deposit away from the boom in our scientific studies at various different distances. We also measure the airborne drift. Let's look at the numbers. If we apply 100% of our spray, as I already said, only about 80% lands under the target, but about another 15% lands very close to the target. We call this swath displacement. This is not true drift. And the remaining 3% goes downwind. And furthest downwind, we really only have 0.3%. It's not that much, but about 1.7% goes into the atmosphere. So this is a problem for trees. It's a problem for the atmosphere. The spray deposit goes down very, very quickly. You can see with distance here, that's a very exponential decay. The material that stays airborne very quickly goes up into the atmosphere. It can go very high very quickly. Just 10 or 20 meters downwind of the spray boom, this spray cloud will already be 5 or 10 meters high. When we look at the amount of spray that does drift, here is airborne drift, here is wind speed. We usually see about 2.5% of the drift is lost from the field, and the power of a coarser spray is very evident. We had a 4-fold reduction in the spray cloud here. So very, very powerful. When we went with a high clearance sprayer, we had a similar amount of drift, even though this is a coarser spray, and we were not able to reduce the drift nearly as much because even when we added a low drift nozzle, and that was because we simply had too high a boom and too fast a travel speed. These are contributing factors to spray drift, and they cannot be easily removed. If we want to get a very low drift, we do have to travel slow and have a low boom. Let's look at an example here of a label. This is Pixaro. It says spray when the wind velocity is 15 kilometers per hour or less, and do not apply when the wind speed is less than 1 kilometer per hour. So I went and looked at a typical summer day. I went to the weather records for Sherbrooke, Quebec. I went to June 5th, 2025, last summer in Sherbrooke, and it was a typical summer day. Here's the wind speed. Here's the time of day. And you can see that the wind is calm. It gets breezy in the middle of the afternoon, and it gets calm again. A typical summer day. If we follow this label and only have 15 kilometers per hour maximum wind speed, we cannot spray in the middle of the day. And so we would spray in the morning or in the evening. If we also follow the label and say, watch the temperature inversions and don't spray during sunrise or before sunrise or after sunset, we further limit this, and we only really have a total of 5 hours of spray time available. Now, if we were to spray under higher wind speeds, we would increase the amount of time available from 4 hours or from 5 hours to 8 hours in total, which is very significant. How do we do this? Well, with low drift nozzles. Low drift nozzles will reduce the amount of drift and will make it possible to spray under slightly higher wind speeds. I do not want to recommend that you violate the label statements, but there is a possibility to spray under somewhat higher wind speeds if you take the proper precautions. The downwind deposit from spray clouds, this is the downwind deposit down here, does not seem to increase very much with higher wind speeds. The airborne drift certainly does, and it does that for both kinds of sprayers. Here again, I do like to use some web assistance that is useful. This is called Windy, and just a few days ago, I did a recording of Windy for parts of Quebec, and I just wanted to show you how interesting it is to see what the weather forecast is like in a graphical way. And so it's quite possible to do some forecasting and plan your spray conditions that way. I want to finish off with just a few words on inversions and go there, and then we'll stop. Inversions, I've sometimes said it's better to spray in wind than in calm conditions. So here's drift damage. This is in the Peace River region of Alberta. someone sprayed onto this canola, and you can see the drift, but you can see that the drift damage didn't go very far. Here's another picture of drift damage. You can see the trees are reducing drift quite a bit, but here the drift came through and the canola is damaged quite badly. This is inversion drift. This is from Manitoba. You can see that it's a much larger area that was damaged by inversion drift. And I just want to explain for a moment what happens with inversions. Inversions typically happen in the early morning. This is a picture from the early morning or late evening and overnight. And during that time, the atmosphere does not mix. So any spray cloud would be very concentrated and would stay concentrated. And so the definition of an inversion is that the air temperature increases with elevation. Usually the air temperature decreases with elevation. And let me explain that to you. So we have a normal decrease of temperature with elevation. Here's temperature, here's elevation. And that, it gets colder the higher we go. That's why there's snow on mountaintops. When the sun shines, the ground heats the air, and then it gets hotter, and then it cools faster. And that means that we have an unstable environment. That means that when we have a parcel of air that rises, it expands because there's less air pressure higher up, and it becomes cooler as a result. But it is still warmer than the surrounding air and tends to keep rising. That's what we call free convection. It's great for dispersing atmospheric pollution. At nighttime, we have the same change of temperature, ideal with height, but at nighttime, the following happens. The ground is colder and it cools the air near it. As a result, the air gets warmer with elevation. And that means that if we take a parcel of air and we move it up, it will expand and cool with elevation, but it will still be warmer than the air around it because it started off warmer. And as a result of that, it will go back down to its original location. And so over the course of a day, if we have, this is again the temperature profile, warmest air at the bottom, cooler air at the top. As we get into the evening, an inversion begins and the opposite temperature profile begins to form. And this inversion grows until sunrise. And this could be 100 meters or more high. And then eventually when the sun rises, the inversion begins to burn off, but there remains an inversion cap. And this inversion cap goes away over time until the afternoon when the inversion is completely gone. So it's a phenomenon that starts in the evening and ends in the morning. Just some pictures to close off. Here's a picture in the morning. This is more or less a neutral atmosphere. Later on that day, I drove past the same place and we have free convection. So that's the inversion is completely gone. Here's another one. Here's some smoke, and you can see the smoke is rising, but it doesn't rise above this level of the air. And as a result, we have some dispersion of the cloud, but not complete dispersion because it can't go higher than this. Here it is later in the evening. The smoke is going up, but not, it basically concentrates. And this is what a spray cloud would do. It would not leave. Here it is under free convection. Okay, so there's all different ways of looking at this. I want to leave you with this video. This is the best video that I've ever seen of an inversion. This is a smoke cloud that was produced on a boom in the morning in Ontario. And look at what happens to the smoke cloud in the early morning hours. This would be spray drift. It would simply hang. It would cause great amounts of damage, possibly over large areas, and it would simply not there's nothing you can do about it. Absolutely nothing. The spray has left, and it is now damaging the crop. We see areas of whole fields very widely damaged from this. So I want to conclude. We're out of time, and say the following. I think a good low drift nozzle is essential for you on your sprayers, and I've identified some. Higher winds cause more drift loss, but not always more drift damage. You want to be very careful with that. Certainly for trees, there is more drift damage with higher winds, but at least in a high wind, you have options for controlling the drift by lowering your boom, go into a coarser nozzle, etc. And low winds during inversions are potentially very, very harmful. So we're out of time. I want to turn it back to our moderator, Marie-Eve. I will stop sharing my screen and perhaps there are some questions.
Yes, thank you so much for your presentation, Tom. It was really clear, and you spoke not too fast. So if people were more interested in following you in English, I think it was really helpful. Nous allons maintenant passer à la période de questions. Les questions, dans le fond, s'ils sont en français, je vais les poser en français, mais certaines sont en anglais. Some questions are in English, Tom, so I will tell them in English, but the first one is in French. La première question, comment déterminer la quantité de sulfate d'ammonium à inclure pour traiter l'eau? I don't know if you want me to translate it to you. How many ammonium sulfate is it necessary to put in the water how to determine how to put the quantity of sulfate ammonium to put in the water?
How much AMS to put into the
Yeah,
water?
yeah. How to determine that?
So the best way to determine that is to use a calculator that I've identified on the website that was produced by North Dakota State. But a rule of thumb, if you want to just have a general rule of thumb, is to use a 1% solution. So it would be 1 kilogram of ammonium sulfate per 100 liters of water. It can end up being quite a large amount of ammonium sulfate, but that is the rule of thumb. 1 kilogram per 100 liters, 1%. That gets rid of most of our water quality issues.
Okay, thank you. The next question is concerning the droplet size. The person is telling, I thought that the advantage of using AI nozzles was that they were producing big bubble droplets able to explode when hitting the target rather than big simple droplets that will run off on the target. Am I wrong?
You're not wrong. You're right. Yes, when we first saw the air induction tips, we were very excited about that feature. So there are air bubbles in these droplets, and they do allow larger droplets to stick a little bit better. This is one of the key features of this nozzle. That is still true. They also have a very unique ability to eliminate the fine droplets. So air induction is great. But I think we have to be realistic. When we compared air induction to non-air induction nozzles that have about the same droplet size, we found the differences were not very great. We found the differences to be acceptable so that we could also recommend non-air induced nozzles and get the same low drift benefits. And of course, that's very important because of pulse width modulation. We can't use air induction with pulse width modulation. So I think I've started to downplay the difference a little bit and have said air induction is great, use it if you can, but if you're using pulse width modulation, non-air induction is also okay.
Okay, thank you so much. The next question is, I don't know if you'll be able to answer that because it's in a greenhouse context. What are your technical recommendations regarding nozzle selection and critical parameters like the droplet size, pressure, or speed to minimize internal spray drift while ensuring effective crop coverage in a greenhouse?
Yeah, of course, in the greenhouse now, I have to say I am not very comfortable with talking about this. I have not worked with greenhouses. But so I don't know whether I'm the right person to answer the question, but
Yeah.
I understand the problem. You know, you need to have small droplets so they move around. They might be circulated with the air ventilation system and so on. I would rather that you seek a different expert for that answer, I'm afraid.
I think it's a careful answer because it's really not the same thing in the greenhouse and in the field. So
Yeah, quite
sorry
different.
for that. We can't give you an answer, but surely people that are working in greenhouses may be more adequate to answer to your question. The next question is really short. I think I don't remember the product, but the question is interlock. Does interlock change the pH of the water? Interlock, is it a
Interlock. I don't know that it does. I don't know if there's anyone here from Winfield United, but I don't believe that interlock changes the pH. The product that does change the pH is Li 700. That is advertised. It is an acidifier, and that's the caution. Interlock, I've never heard that it changes the pH. So I think it is a little bit safer to use in that regard.
okay? Next question. Does your recommendation to use coarse or very coarse droplets apply only to herbicides or also to fungicides and insecticides?
That's a great question. We have studied droplet size with fungicides a lot, and we were very surprised that the larger droplets also worked well with fungicides. We did not expect that. We compared hollow cone nozzles producing a very fine spray, twin nozzles producing a very fine spray, to coarse nozzles, and we found similar, statistically identical amounts of disease control. We felt that for disease control, it was much more important to focus on the timing of the application and to focus on the water volume of the application. So I was actually very happy to find this result. We have this result with sclerotinia in canola. We also had it with diseases in lentils and peas. We've had similar results in soybeans. And the reason I'm happy about this is that it allows us to maybe use a coarser spray, of course, with enough water, and then get more time to do the spraying because it's a little bit less sensitive to wind or heat, which is an advantage.
Yeah, and does it mean that you don't have to change nozzles too often if it does well with herbicides and fungicides at the same time?
That's correct. Yeah, it simplifies your whole operation because you can keep the same nozzle. Now, another thing I should say, I'm not sure if any of the people on the webinar are in a fusarium head blight region, but where there is fusarium head blight, and we typically use these twin nozzles that spray forward and backward. In that case, we have good evidence that the coarser sprays are better than the finer sprays because the angle that they fly is more it stays longer so that the impact on the wheat head can be from the side, which is necessary.
Okay, really good. The next question, will AMS, ammonium sulfate, increase volatility with 2,4-D like it can do with dicamba?
We do not have any evidence that the volatility of 2,4-D is affected by AMS. We believe it is not. 2,4-D is, of course, much less volatile than dicamba is, particularly 2,4-D amine and particularly 2,4-D on the enlist label. And we have not seen any evidence that a lowering of the pH or the addition of ammonium sulfate is a problem for 2,4-D.
Okay, that was the last question, and I think it's really good because we are going to be in just in time. So that's not it wasn't that great that you passed your time for your presentation. So I'll go to the close of the webinar. Alors, je remercie tout le monde pour votre participation, pour les questions très intéressantes que vous avez posées. Donc, un sondage d'appréciation vous sera envoyé après le webinaire. Votre appréciation, le résultat du sondage et vos commentaires seront pris en considération pour de futures activités. On s'excuse aussi là, pour les petits enjeux du début. On a eu des petits problèmes techniques ce matin, mais on espère qu'au moins pour ceux qui ont manqué le début du webinaire, vous pourrez y avoir accès. Là, vous pourrez y avoir accès là, par la suite, puisque c'est au moins enregistré et rendu disponible. Et la présentation aussi pour ceux qui posaient la question plus tôt. Mais avant de vous laisser, j'aimerais prendre un dernier moment pour remercier à nouveau notre conférencier, M. Tom Wolfe, spécialiste des traitements par pulvérisation et consultant chez Agrimetrix Research and Training, Thank you again, Tom, for your presence and for your clear presentation. I saw you can go, maybe you can, I think the chat, the comments in the chat were wrote mostly in English, but I think this is a great success. Nous vous invitons à visiter la page web du craaq dédiée à l'événement où vous trouverez prochainement la date du prochain webinaire de la série. Merci encore à toutes et à tous pour votre participation et au plaisir de vous retrouver lors du prochain webinaire. Bonne journée à tous.